All attendees are in listen-only mode.
Good afternoon, and thank you for joining us today as the National Board of Public Health Examiners presents the final in our series of 5 webinars geared to explaining the certification in public health credential and to help you prepare for the upcoming exams. Each of our sessions are 2.5 to 3 hours long and include a presentation, the lecture component, as well as some interactive segments. A break will be offered midway through the presentation, and there will be periods for questions and answers as we move along. This presentation will be archived on the National Board of Public Health Examiners website, as well as the other webinar sessions that we've presented earlier in the year. Today's session feature is on biostatistics. We are pleased to have Dr. Lisa Sullivan, Professor and Chair of the Department of Biostatistics at Boston University School of Public Health. Dr. Sullivan, thank you for joining us today.
Thank you, and welcome everybody. I do apologize that we had to reschedule this presentation. Unfortunately, we've had a lot of snow in the Boston area, and so it's been quite challenging here. So what I'd like to do is walk you through an overview of biostatistics, the core area of biostatistics, and as we go through, talk about terminology and definitions. And what I've done is insert some practice questions as we go along, and you may have seen this format of questions in a course where the instructor would pose a question. They're all multiple choice, and I use these kinds of questions in teaching this class with students and the audience response, or the clickers. And obviously we don't have the clickers available right now, but I thought they might just keep you engaged in this. It's difficult to sit and listen for this amount of time. So I'll just throw a few questions up as we go along, hopefully give you a little practice on the topics that we're talking about. As Erin says, please feel free to submit questions, and we'll take breaks periodically, and I'll try to answer all the questions that you have. So there are two areas of statistics: descriptive statistics and inferential statistics. And I'm making this distinction because sometimes when people go through descriptive statistics, they don't pay much attention. You calculate a mean or a standard deviation and move on from that. And really the application of biostatistics is in the inferential side, where we're making inferences about a population based on what we see in our sample. That's really the fun part of biostatistics, but we have to do the descriptive piece first, and in fact, an important step is identifying the kinds of variables that we're dealing with. And this is extremely important because in biostatistics, the type of variable that you're analyzing dictates the kinds of analyses that you'll do. And so it's really important that you get this straight. In fact, it's one of the areas that people probably make the most mistakes in when they do biostatistical analysis. So depending on the kind of variable that you're analyzing, that determines what kind of summary measures you use and also what kind of statistical tests that you use. So we can organize variables into a couple of different types. And within these, there are more detail that we could delve into, but these are really the broad categories. So dichotomous variables, sometimes called indicator variables, have two possible responses. And these come up a lot for us in medicine and public health, where we look at whether people have a disease, yes or no, they develop a disease, they were exposed to a certain risk factor, yes or no. So we analyze dichotomous variables quite often. Ordinal and categorical variables have more than two response categories, and for ordinal variables there is an ordering to those categories, and categorical, sometimes called nominal variables, are not ordered. So an example of an ordinal variable might be disease stage. So often when a patient is diagnosed with cancer, they will be categorized as stage 1, 2, 3, or 4, and those are discrete categorizations, but there's definitely an ordering in terms of severity to those different categories. And then continuous variables, sometimes they're called quantitative or measurement variables, assume in theory any value between some theoretical minimum and maximum. And so, again, we see a lot of variables that are continuous in our work, things like age, cholesterol level, all of those tend to be continuous variables. So just to be sure about this, so here's one of these questions that I was mentioning. We want to study whether individuals over 45 years are at greater risk of diabetes than those 45 years and younger. What kind of variable is age? So I'll just give you a second to think about that. So for this one, in this case, the age variable would be a dichotomous variable. Usually age is a continuous variable, but if we're categorizing people as over 45 versus 45 and younger, this would be operationalized or analyzed as a dichotomous variable. How about this? We are interested in assessing disparities in infant morbidity by race ethnicity. What kind of variable is race ethnicity? So here, hopefully you thought of this as categorical. There are many different race ethnicities that we could think about. We could spend the next 3 hours discussing those, but there's no ordering to them. There are a number of discrete categorizations, and lots of times when you have a question such as this on a survey or you collect information like this, you often have the question posed as which of these best describes you, because it's hard to actually delineate all the possible responses. And then you often have an other category where people don't find themselves fitting neatly into one of the ones that you've described. But these are important to identify the correct variable type, because depending on the variable type you're analyzing, that dictates how you summarize and then do statistical inference for those variables. So if you've got a dichotomous, categorical, or ordinal variable, one of the best ways to summarize that variable numerically is with what we call a frequency distribution table. So here I've got a variable health status with 5 response options, and they are ordered. So this is an example of an ordinal variable. The frequencies are the counts, the number of people who endorsed each of those different categories. The sample size, n, is 50. And probably the best summary for this variable is the relative frequencies, shown here as percents. You can show relative frequencies as percents or as proportions, numbers between 0 and 1. But note that the relative frequencies sum to 100%, or if they were shown as proportions, they'd sum to 1, because each person is represented exactly once here. If you have an ordinal variable, such as we do here, 2 additional columns, I've kind of grayed them out because you could use this same format if you had a categorical variable. But here I'm also adding cumulative frequencies and cumulative relative frequencies, where you can think of these as running counts and running percentages. So just going down the rightmost column, 38% of the people reported their health status as excellent. 62% reported their health status as very good or better. 80% reported health status as good or better, and so forth. When you get down to the last response, in this case poor, the cumulative frequency is 50 because everyone has been accounted for with the response poor or better. In terms of graphical displays, a frequency bar chart, now I'm going to make the distinction between a bar chart and a histogram in just a minute. A bar chart such as this would be used to display a categorical variable. So marital status is an example of a categorical variable. And in this case, we've offered 5 different response options. Again, there are different ways to ask this or collect this kind of information, but people are indicating whether they're married, separated, divorced, widowed, or never married. And this is what's called, or what's showing here is a frequency bar chart, because on the y-axis, the vertical axis, we're showing frequencies or counts. When you have a categorical variable, the different response options are separated by a space, because these are unordered, and in fact, we could reorganize the response options any which way. We could order them alphabetically from most to least frequent, whatever we wanted, and that would not affect the interpretation. In contrast, this is a histogram for that health status data. A histogram is used for a ordinal variable because there is an ordering to the response options. And just to show you a different display, this is what's called a relative frequency histogram, because on the y-axis we're showing percentages or relative frequencies. You can produce a relative frequency bar chart or a frequency histogram. And so relative frequency or frequency is dictating what shows on the y-axis. The x-axis here shows the different response options for the health status variable. I'm showing the responses going from poor to excellent as you go left to right. You could go the other way and start with excellent on the left side and going down to poor, but you can't reorganize these categories in any other way, alphabetically, for example, because there is an ordering and we have to maintain that. So with a histogram, the bars run together, the idea being that there is an underlying continuum here running from poor through fair, through good, all the way up to excellent. So when the categories are ordered, the bars run together. That's a histogram. When there is no ordering, then you show the responses as a bar chart with space in between. Continuous variables, as I noted, sometimes they're called quantitative or measurement variables, assume in theory any value between some minimum and maximum, and that depends on the scale of measurement and what you're dealing with. So an example might be systolic blood pressure. And a standard summary for a continuous variable is the sample size. Suppose we have 75 people. The sample mean, that's X bar, and in my sample, the sample mean is 123.6, so that represents a typical blood pressure in my sample, and the standard deviation is 19.4. And those three summary statistics tell you what you need to know generally about a continuous variable. So I'm just showing a second sample. It's got the same sample size, and in general, you want to see the sample size because you want to have a sense of how large the data set is and how much weight you should put on that particular sample in terms of making inferences about populations. The larger the sample, generally, the more confidence we have in the results because it's based on more people. But there does come a point where adding more subjects or increasing a sample size doesn't gain you much more precision. But generally speaking, the larger the better. The second sample has a sample mean of 128.1. So just if you were comparing samples, the second sample on average has blood pressures that are a little bit higher by about 5 milligrams of mercury. And the standard deviation in the second sample is 6.4. Usually people have a harder time interpreting the standard deviation. It's a measure of variability among observations. So in the first sample, the standard deviation is 19.4, meaning that on average, the observations, the blood pressures, deviate or vary from the sample mean by about 19 units. And that's either way, above and below. In the second sample, the standard deviation being smaller tells us that the observations are much more tightly clustered around the mean, deviating only about 6 millimeters of mercury above and below on average. So the smaller the standard deviation, the more tightly clustered the observations are around the mean. So there are other measures to summarize a typical value and variability in a sample. And usually the sample mean and the standard deviation are the standard measures of a typical value and variability, but those work very well when the sample is not subject to outliers or extreme values. So if you don't have extreme values, and those could be values that are extremely high relative to the others or extremely low, then the sample mean and the standard deviation are good summaries of a typical value, or in statistics we call that location, and variability. But when there are outliers, so say in the systolic blood pressures that most of the values were around the 123 or the 128, but you had a person who had extremely bad hypertension and their systolic blood pressure was in the 200s. That value in a reasonably sized sample could pull the sample mean up in such a way that it's no longer representing a typical value. So if you do have outliers, then usually people shift to presenting the median and what's called the interquartile range to summarize a typical value or location and variability. The interquartile range is the difference between the first and the third quartiles. So just to remind you, the first quartile is the value that separates the bottom 25% of the data from the rest. The third quartile separates the top 25% of the data from the rest. The first quartile is sometimes called the 25th percentile, and the third is the 75th percentile. The difference between those captures the middle 50% of the data. And so that's a measure of the variability in the sample when you look at the distance between the first quartile and the third. The median is the middle value, so it separates the bottom 50% from the rest. I'll show you a data table where people present these different kinds of statistics. So the question as to how do you decide mean, standard deviation versus median interquartile range is dependent on outliers. And there are several ways to identify outliers in a sample. One way is based on your clinical or substantive knowledge of whatever it is you're measuring. If you look at a sample you, if you're an expert in this particular area, might be able to say this value or that value is extreme relative to the others. And that's perfectly fine. There are a couple of guidelines that people use, and I'm saying this not as rules, but guidelines that people use to identify outliers. One is outliers are defined by values that are lower than, less than, the first quartile minus 1.5 times the interquartile range. So that would identify outliers on the low end. And on the high end, values that exceed the third quartile plus 1.5 times the interquartile range. So this particular formulation is what's used in many statistical computing packages. You may have used SAS or R or Stata or something else. This tends to be what those packages use to identify outliers, and it's called Tukey fences. These formulas are what are called Tukey fences. You're putting a fence around what you think are values that are reasonable, and these limits, the low one and the upper one, identify values that might be extreme. And so here's an example of a Table 1. We often see Table 1 in papers summarizing background characteristics or baseline characteristics of subjects in a study. This happens to be a study looking at soft drink consumption and relating it to cardiovascular outcomes. But here you see first for the variable age, which is a continuous variable. Now, this table went on a bit further than I'm able to show on this slide, but at the bottom of the table there was a footnote to indicate that for continuous variables that you're seeing means plus or minus standard deviation. So what's being shown here is the mean age and the standard deviation of age in each of the soft drink categories. What's also important to note are the sample sizes. You always want to look at those when you're looking at summary data in a table. And I just want to point out down at the bottom, you see the variable triglycerides. Once again, you're seeing means and standard deviations. Now, when you look at those means and standard deviations, if you see a situation where the standard deviations are very large relative to the means, that's usually a flag that you might have outliers. And so in this case, the fact that the standard deviation is in the hundreds for the last two categories suggests that there are possibly some outliers or extremely high values among the triglycerides. And this might have been a candidate to present the median in the interquartile range. And so that's another way to look at or to identify whether there might be outliers. And one last way is if you have the opportunity, if you're analyzing data by computer, to calculate the mean and the median. If the mean and the median are close in value, that would suggest that you have no outliers. If the mean and the median are quite different, then that's an indication that you have outliers, and obviously the mean is being affected by those outliers. And if they're quite different, then you would want to present the median in the interquartile range. In terms of graphical displays for continuous variables, a popular one is called the box and whisker plot. Now, I've added all of those labels running across the top of the figure. I just want to point out what's what in this picture, but the figure itself just consists of the horizontal line and the box. The horizontal line represents the range of the data, the minimum to the maximum. The leftmost vertical line is the first quartile. The median is the second vertical line, and the third quartile is the third, the rightmost vertical line. So there are really four sections of this graph, and each of those sections essentially represents 25% of the participants. And because the first quartile separates the bottom 25%, the median is the halfway point, and the third quartile is the 75th percentile, or separating the top 25%. So if those four sections of the graph are essentially equal, that suggests the data are pretty symmetric. If the box is pushed down to the low end or scrunched up in the right end, that suggests that there's a lot of skewness in the data. If the entire box was shifted, say, to the left, and you had a long tail on the right, that would tell you that most of the data, 75%, are in the low end, and then you have some people that spread out over a longer range. that would be called data that are skewed to the right. You say to the side with the long tail. These kinds of plots are also useful for comparing samples. So here I've got a red sample and a black sample. The black sample is number 1 and the red sample is number 2. So when you show distributions side by side, you can make comparisons of the two. So what comes across from this comparison is that the medians are different in the two samples. In sample 1, the median blood pressure might be 121. So in sample 1, see that middle bar, that if you project it down onto the scale, it's around 121, as compared to the median in sample 2 might be around 130. So here, the box in the middle contains the middle 50% of the data. So if you had to summarize the comparison between the two, the blood pressures in sample 2 on average are higher than the blood pressures in sample 1 because the middle 50% are shifted to the right. You can also make statements like this. 75% of the blood pressures in sample 1 are 130 or below, as compared to only 50% of the blood pressures in sample 2 being 130 and below. Lastly, the variability in the red sample is a little smaller than the variability in the black sample, and that's indicated by the red line, the range from minimum to maximum. So it's not quite, the data don't vary as much in sample 2 as they do in sample 1. Okay, so a couple of just test questions to practice some of this. And again, these are the types of questions that you might see on the exam. So what kind of display is shown below? So in this one, what you see is patients by disease stage. Disease stage is categorized 1, 2, 3, 4. So that would be ordinal. So this is a histogram, and you can also tell that by the bars running together. And now you have to look at the y-axis to see what's shown to distinguish between responses 3 and 4. What's being shown on the y-axis are percentages or relative frequencies. So this is a relative frequency histogram. This distribution is blood pressure, systolic blood pressure in men 20 to 29 years of age. If this were the distribution, what would be the best summary of a typical value? So here, if the data are symmetrically distributed, as they are here with this bell-shaped curve, the mean would be a better measure than the median. The median would come into play if you had a more skewed distribution. The interquartile range and the standard deviation are summaries of variability, not of typical values. Again, another term for typical value is location. When data are skewed, the mean is higher than the median. So here the correct answer would be false. It depends. It depends on whether the extremes are on the high side or the low side. If you have an extremely high value, that would pull the mean up higher than the median, and vice versa if you had an extremely low value. Suppose you had data distributed this way, showing the box whisker plot, what would the best summary of variability be? And in this case, it would be the interquartile range. The long tail on the right suggests that there are some extreme values on the high side, assuming the data are organized low to high, and so the interquartile range would be the best summary of variability here. So just to summarize, numerical and graphical summaries depend on the kind of variables that you're dealing with. Dichotomous, again, another word is indicator and categorical variable. Frequencies, another name for counts, and relative frequencies, often shown as percentages, are the best numerical summaries. Bar charts, either frequency or relative frequencies, provide the best graphical summary. If you have an ordinal variable, you can look at frequencies, relative frequencies, cumulative frequencies, and cumulative relative frequencies, depending on the kinds of summary statements you'd like to make. Histograms are the best graphical summary for ordinal variables. For continuous variables, the sample size is always important to present, and then either the sample mean and standard deviation or the median, and the interquartile range. And you use the latter two if you have outliers. Again, determined by a rule, like the one I gave you based on the quartiles, or by your judgment. And then a box whisker plot is probably a good summary for a continuous variable. Okay, so now we'll shift over to some probability, usually everyone's least favorite topic in the biostatistics course. But I'll just do this through a few practice examples just to remind you of how we work through probability. So what is the probability based on the data shown below, and I'll walk you through that, of selecting a male with optimal blood pressure? So what you're seeing in this table are people categorized by their blood pressure, and here we're showing them as having optimal, normal, pre-hypertension, or hypertension. Those are the blood pressure categories running as columns in the table. And then we have men and women, a total of 150 people categorized. So the question is, if we were to select a person at random, what's the probability we select a male with optimal blood pressure? So the correct response here would be 20 out of 150. And the other two responses that I've put here actually answer different questions, and I'll just walk through those quickly. So looking at the 20 out of 25, that would answer the question, what proportion of people with optimal blood pressure are male? That wasn't what was asked, although the difference is quite subtle. The question number 2, or the answer number 2, is answering the question, what proportion of men have optimal blood pressure? So the idea is the first two responses are responses to questions that deal with conditional probability, looking specifically at a certain category of blood pressure or at a certain sex group. The question that was asked was, what's the probability of selecting, and it doesn't say this, but it's implied, from among the whole pool, a person who is both male and has optimal blood pressure. And that's why I'm using my total size, 150, as the denominator. Here's another one. What's the probability for the same data of selecting a patient with pre-hypertension or hypertension? The correct response would be the first one. There are exactly 95 people, 40 from the pre-hypertension category and 55 from the hypertension category, who fit into the pool that we're asking. And again, we're asking from among the whole pool. We're not saying just look at the men, just look at the women. What proportion of men have prevalent CVD? So here you need to compute the totals, and if you're working across the rows, 35 plus 265 is 300. There are a total of 300 men. So you have to read this question carefully. What proportion of men have prevalent CVD? So it would be exactly 35 out of 300. It turns out there are 700 people represented here when you put in all the totals, but the question is asking just looking at the men. And so this is an example of a conditional probability, looking only at the subset of men. What proportion of patients with CVD are men or male? And here the response would be 35 out of 80, looking just at the people with CVD. So again, this is a conditional probability, and what it means to be a conditional probability is you're conditioning on a certain characteristic, or in other words, focusing, subsetting on a particular group. So looking just at those with CVD, that's the people represented in the first column, and they sum to 80. What proportion of those 80 are male? 35 out of 80. So this idea of conditional probability comes up when we're asking questions like, are certain characteristics related to other characteristics? And often the question is posed this way. Are, in this case, family history and current cardiovascular disease independent? Does your likelihood of having cardiovascular disease yourself depend on whether you have a family history? So here's a little table showing whether individuals have a family history of cardiovascular disease, yes or no. Those are the rows of the table. And then whether they themselves have current cardiovascular disease. And the question is family history related to current CVD? Well, it's hard to get at that looking at these numbers here. What we need to do is calculate a few conditional probabilities. So the probability that someone has CVD, current CVD, given, that's the vertical line, given they have a family history, is 15 out of 105. So the people who have a family history are those shown in the second row of the table, the 90 plus 15, so that sums to 105. Among those, 15 have current CVD. So among those with a family history, 14% have current CVD. In contrast, the chance that someone has CVD given they have no family history would be 25 out of 240. Now we're looking just at the first row of the table, and that's 10%. Is there a relationship? Yes. If you have a family history, you are much more likely, 14% chance, as compared to a 10% chance, of having cardiovascular disease yourself. So it takes calculating these conditional probabilities and comparing them to decide whether characteristics are related, dependent, or not, independent. So here's a question. Are symptoms independent of disease? So again, you've got to do some calculation. So if you look at those who have symptoms, that's 250, exactly 25 also have disease, so that's 10%. Among those with no symptoms, there are 500 such people, 50 of them have disease, that's also 10%. So in this case, we would say symptoms are independent of disease. So you make the comparison of those conditional probabilities, and if the probability of disease is the same for those who have symptoms and for those who don't, then we say there's no relationship or they're independent. There are also other probability models, or lots of probability models that you might have seen in your exposure to biostatistics. I'm not going to go through them in lots of details because I think the nature of the test and what I think many of us hope you get out of an introductory biostatistics course is an understanding that there are lots more details to get into, but just understanding where those details might be different. So for example, you may have been exposed to a binomial probability model or a Poisson probability model. These come up for us a fair amount in public health and in medicine because for the binomial, the outcome is the success failure, yes, no type of outcome. So we do see that a fair amount. And the binomial, two response categories, we're looking at a fixed number of replications, and we're assuming that relationships among the replications are independent. So let me give you an example. We might be looking at a certain type of disease. So if people have the disease, people either have the disease or they don't. So that fits the success failure, the two different response categories. What we could do is ask a question like this. I have a panel of patients, maybe 50 patients. That's a fixed number of, we call them trials, but for us often it's looking at individuals. And the likelihood that any one patient has the disease is independent, not related to the likelihood that any other person has the disease, assuming that they are not brothers and sisters or otherwise related. We could ask a question like, what's the probability that I see 10 people out of 50 experiencing the disease? That could be answered with a binomial probability model. The Poisson probability model deals with an outcome that is a count. And often that comes up when we're looking at exposure data, maybe some environmental exposure information. So we have people that are exposed or not, and we ask questions like, looking at a large group, maybe they're of communities or of individuals, what's the likelihood of observing a certain number who have been exposed versus not? So it's similar to the binomial. The difference is that there could be more than two response categories, and often we're looking at larger numbers of replications. What you probably have done a fair amount of work with is a normal distribution. This is a model for a continuous outcome, and we talk about this in many intro biostat courses because it underlies a lot of the statistical inference that we deal with. So the normal distribution is the bell-shaped curve. It is a model for a continuous outcome. And it turns out that many of the characteristics that we deal with actually do follow a normal distribution, even though this seems kind of specific. And the idea of a normal distribution is lots of people have values around the middle of the distribution. As you move to the extremes, on the high side and on the low side, you have fewer and fewer people. For the normal distribution, it has certain properties. The mean is always equal to the median, is always equal to the mode. We've talked about mean and median, but the mode is the most frequent value. So the mean is sitting right in the middle of the distribution. And the mean is also equal to the median, tells us that half of the values are above the mean and half of the values are below the mean. That's the definition of a median. The highest peak on the curve, that's the mode, is also where the mean is sitting. There are a few other properties of normal distributions. The distribution is symmetric about the mean, so the right side looks like the left side. The probability that a person has a value exceeding the mean is the same as the probability that they have a value falling below the mean, and in both cases it's 50%. That's the definition of a median. The mean and the variance completely characterize the normal distribution. What that means is if you know those values, you know everything about the distribution. You can calculate any probability if you know the mean and the variance. And I mentioned the mean, the median, the mode. And it turns out for a normal distribution, about 68% of the values fall between the mean plus or minus 1 standard deviation, 95% of the values between the mean plus or minus 2 standard deviations, and almost all between the mean plus or minus 3 standard deviations. So oftentimes people use the normal distribution to look at laboratory tests. And the fact that 95% of people fall between the mean plus or minus 2 standard deviations is often used to define what we call normal limits. So you might go to a doctor and have a physical exam, and they take blood and measure lots of things in you, and you get a report back a couple of weeks later, and it says, here were your results, and it might say for this or that characteristic you are within normal limits, and then for something else you might get flagged, and it might say you're outside of normal limits. It doesn't mean that that value is bad. It just means that you might be outside of that 95% that's in the middle of the distribution. It does not suggest that something is definitely wrong. It just means that you're outside of 95%, and often that triggers more testing to just be sure that something isn't wrong in that case. So a quick example, body mass index for men age 60 is normally distributed with a mean of 29 and a standard deviation of 6. Now, if we looked at body mass index for men and women combined, we might not have a bell-shaped or a normal distribution. There might actually be 2 peaks, one for men, one for women. If we also looked at BMI for people of varying ages, even if they were of the same sex, they may also be different. But if you focus on a particular sex and age group, data tend to be normally distributed. So once I know something follows a normal distribution, I can draw the bell-shaped curve, and I can also plug in the mean right in the middle of the distribution. And then the fact that almost all the values are between the mean plus or minus 3 standard deviations tells me I can count out in units of the standard deviation, so by 6s, 3 standard deviations above, so to 35, to 41, to 47, and that should place me at the end of the curve. Starting at 29 and backing off, subtract 6, subtract 6, subtract 6, that should put me at 11. That doesn't mean that no one has a BMI lower than 11, although that's quite unlikely, or someone doesn't have a BMI over 47. Unfortunately, that does happen, but they're just unlikely to happen because most of the people are within this range. Now, you probably went on to calculate probabilities with the normal distribution. I just want to remind you, on the exam, we're not going to be having you do lots and lots of calculations, but given what you understand about the normal distribution, you can probably, from a set of multiple options, figure out which response is most likely true. So here, what's the probability if we select a person, a male, that person has BMI less than 29? Well, 29 happens to be the mean value, so that would be a value of 0.5. 29 is exactly in the middle. A more realistic question might be, what's the probability that a male has a BMI less than 30? Well, 30 is just a little bit above 29, so it's a little over 50%. The way we solve that exactly is we shift over to the standard normal distribution. We convert our question about BMI into a question about the standard normal distribution. And you had in your statistics book or access to through the computer a table of probabilities for the standard normal distribution. So we're asking about a BMI, that's an X value of 30, that translates to a Z-score of 0.17. So if you think about where does 0.17 fall on the normal distribution curve, well, it's just a little bit above 0. That's exactly where 30 was when we were looking at the distribution of BMI. So if you had access to a table, the table would tell you, or a computing package would tell you, that that probability is about 57%. Once again, you can probably guess that if you were given several options, understanding what you understand about a normal distribution curve. Other things that we do with normal distributions is we make comparisons. So think about this. Suppose we're looking at blood pressures, and we ask the question for, or let me back up. Suppose for men age 50, blood pressure is approximately normally distributed with a mean of 108 and a standard deviation of 14. For females of the same age, blood pressure is normally distributed with a mean of 100 and a standard deviation of 8. So picture those two distributions. Now the question is, if a male age 50 has a blood pressure of 140 and a female age 50 has a blood pressure of 120, who has the relatively higher blood pressure? So the question being asked is, which is worse, 140 for a man or 120 for a woman? In absolute terms, 140 is higher, but the question is 140 worse for a man than is 120 for a woman? So we're comparing apples and oranges because the distributions are different. So what we have to do is put things on the same scale, and one way to do that is by converting these into z-scores. So that 140 for a man is actually 2.29 standard deviations above the mean for a male. If we do the same with the 120 for the female, we find that that value 120 is actually 2.5 standard deviations above the mean when you look at the distribution in women. So the 2.5 would be the more extreme value. So this is a way to make a fair comparison between the two by standardizing, putting them on the same scale. The last thing that we do with normal distributions, and you've seen this in when you took standardized tests for maybe applications to graduate school, are calculate percentiles. The kth percentile is defined as the score that has a certain percent, k percent below it. So the 90th percentile is the score that has 90% of the scores below it. The first quartile is actually a percentile, the 25th. The median is the 50th, and the third quartile is the 75th. Here's a little formula that allows you to calculate percentiles. It essentially takes that Z formula and calculates a score from it. So X represents the percentile that you're interested in. Mu is the mean of the variable that you're talking about. Z is a value from the standard normal distribution for whatever percentile you're after. And sigma is your standard deviation. So for example, if we asked what's the 95th percentile of BMI for men, you could use this little formula. It's 29. That was the mean that was given. 1.645 is the Z-score for the 95th percentile. You multiply that by the standard deviation, and it's 38.9. The interpretation is that 95% of the BMIs are at or below 38.9. 5% of the BMIs among men would exceed that value. The last thing that we all often talk about when we talk about probability is something called the central limit theorem. And it is a statistical theorem, so we can go into this in great detail. I'm not going to do that, but I'm going to tell you why we even bring this up and what we use it for. What it says is, and there's a very elegant statement of the theorem, but I'm going to tell you what we use it for. What it says is, if you have a population, it doesn't have to be a normal population. It can be a population of any shape, as long as you know the mean and the standard deviation. Now, we'll never know that in practice, but in theory, it could be calculated, or they could be calculated if we had access to the population. if you take samples of size n, that sample size might be size 50 or 100 or 20, whatever you think is reasonable. As long as your sample size is large, and it's been shown empirically with computer simulations that usually a sample size of 30 or so ensures that this result follows, then it turns out if you graph all possible sample means, that is, you looked at every possible sample of the size that you're considering, it turns out that the distribution of the sample mean is approximately normal. Now, why do we care if the distribution of the sample mean is approximately normal? Because when we do statistical inference, we usually calculate the sample mean as a predictor of the unknown population mean. Knowing that something follows a normal distribution tells us a lot about that particular characteristic, and we can calculate any probability we want once we understand that something follows a normal distribution. So this is a second Z formula that I'm showing here. It's not exactly the one I showed you a second ago when we were doing the BMI examples, because this Z formula converts an X bar value to a Z score. And you, again, subtract the mean, and you divide by the standard deviation of X bar. So the denominator here is sigma over square root of n. That thing is called the standard error. The standard error is sigma, the standard deviation, divided by square root of n. Lots of times people have confusion about standard deviation versus standard error. Standard deviation measures variability among observations, person to person. The standard error measures variability among a summary measure, in this case a sample mean. So if you look just at that standard error, it's sigma over square root of n. As the sample size n goes up, the standard error goes down. So if you take samples that are larger in size, then the standard error, or in other words the variability, one sample mean to the next, will be smaller. Often in tables, when people present summary results, they'll show you the mean of some particular characteristic that they're estimating and the standard error. And they're trying to give you a feel for the sampling variability. That's what the standard error is getting at. All right, this is a reasonable break point before we get into the statistical inference. So if it's okay with everybody, we'll take a 5-minute break or so. If you need to stretch, go get a drink or whatever, and we'll look at a couple questions, and then we'll reconvene in 5 minutes or so and go through the rest of it.
Lisa, we don't have any questions that have been submitted at this point. So if anyone does have a question, please, and during the break, just enter it into the question box, and we will answer it on our return. So we will see everyone at about 12:55. Thank you.
Thanks. Are we still on?
Yes, we are still on, Lisa.
Okay. I mean, you think it's going okay? Am I too fast, too slow?
Actually, everyone is still live in the presentation. I think you're doing great. I think you're doing great, though. But I will send you a quick message in the chat box.
Okay.
Bye-bye.
We back?
Okay, Lisa, I think we're back.
Okay. Now, Elliot, I'm switching slides and they're not moving. Maybe I needed to do that. Okay, I'm back. I got it.
Okay, good.
Sorry about that. Okay, so please feel free to ask questions if you have any. You know, I'm happy to stop if I'm going along too fast or if I'm going too slow. Tell me that too, and we'll march along. Okay, so now let's shift gears into statistical inference. So there are two areas of statistical inference, estimation and hypothesis testing. With estimation, the idea is the population parameter, like a mean or a proportion, is unknown, and you use the sample to generate estimates. With hypothesis testing, we actually start at a different place. We know something about the population so that we can formulate a hypothesis about that parameter, and then we take a sample and see if the sample statistics either support or refute that hypothesis that we come up with. So we'll walk through each type. Now, whether you're doing estimation or hypothesis testing, the type of variable that you're dealing with dictates the analysis, the same as it did for descriptive statistics. So you first, when you look at a problem, and this, you'll have to do this, you do this in practice, look at what kind of outcome variable am I dealing with, something that's continuous, dichotomous, categorical, or time to event. Now, we didn't talk about that so much, but I'll bring that up in a little bit. So then the second question is, how many groups do I have? Do I just have one group and I'm trying to make a statement about that one group, or am I comparing two independent? Now, I'm using the word independent here as physically separate groups. So think of a clinical trial where some people get a drug, some people get a placebo, different groups. Two matched groups, or paired sometimes they're called, and that could be like a before and an after measurement on the same individuals. Or do you have to identify the nature of your outcome variable and the number of groups and the relationship among the groups? That will dictate the kind of analysis that you do. So those first two questions will get you a long way, or answers to those first two questions will get you a long way. Then there are lots of questions that we ask that are getting at associations between variables. And there we get into regression analysis. And we'll talk a little bit, I'll remind you of linear regression, logistic regression, those kinds of things. Okay, so back to estimation. So the idea of estimation is we're determining likely values for an unknown population parameter. There are two kinds of estimates. A point estimate is the best single number estimate for some unknown quantity. That's a good starting place, but usually not sufficient. So we usually start with the point estimate, and then we move to a confidence interval, which is a range of values. And the form of the confidence interval is the point estimate plus or minus of what we call a margin of error. And I'll remind you of what that looks like. There are actually two things that make up the margin of error. A t-value or a z-value representing your level of confidence that you choose, and then the standard error, an estimate of the variability of the statistic that you're using. We'll go through some examples. When you do hypothesis testing, I always think of a set of steps. You set up your what we call null and research hypothesis. Just to remind you, the null hypothesis is what you think, the null hypothesis is the no change situation. The research hypothesis is what you think is happening. By doing an intervention, you think there's going to be a change in a certain direction. You also select alpha, which is your level of significance. Usually the level of significance is 5%. Nothing sacred about that, but usually that's the value. You choose a test statistic, and that depends on the kind of variable that you're analyzing and the number of groups that you're analyzing. You set up a condition to help you decide, do I believe the null hypothesis or the research hypothesis? You look at your data and you draw a conclusion. And usually we summarize the significance from a statistical standpoint with what's called a p-value. And if you do this by computer, which most of us do, it automatically spits out this p-value, which helps us to summarize statistical significance. So a p-value represents the exact significance of the data. And usually we estimate the p-value when we reject the null hypothesis, or we can approximate it with statistical tables. But just in general, it's this last bullet that's important. If the p-value is less than or equal to alpha, which you choose, and oftentimes alpha is 0.05, then you reject the null hypothesis in favor of your alternative, which is what you most of the time hope is the case. When we do hypothesis testing, we are almost always hoping to reject the null hypothesis, the null being the no change, no difference situation, in favor of the alternative or the research hypothesis, which is what we think. If we run a test and the level of significance is very small, what that's saying is the likelihood of observing the data that we observed, given the null hypothesis, is very, very small. So it's unlikely then that the null hypothesis is true, so we reject it in favor of the alternative. So we want the p-value to be small. That's supporting what we think, which is the research hypothesis. Now, when we do statistical tests, there are a couple of mistakes that we can make, and these are important to recognize. So in this two-way table, in the rows of the table, I'm indicating HO, the null hypothesis, is true. HO, the null hypothesis, is false. So the rows of the table indicate the true state of nature. Either in nature, the null hypothesis is true, there is nothing going on, or things are as they were, or the null hypothesis is false. What we have done to intervene has made a difference. Unfortunately, we will never know for sure whether the null hypothesis is true or false because the population is large, we can't get at everybody in the population. So what we do is we take a sample and run a statistical test. That statistical test tells us to either reject the null hypothesis, the rightmost column, or not to reject the null hypothesis based on where the data fall relative to our rule that tells us how to make a decision. If we are in the rightmost column, the data tell us to reject the null hypothesis in favor of the alternative. One of two things has happened. Either in the bottom right corner, we are correct, we rejected the null hypothesis, and the null hypothesis is false, that's a correct decision. Or we rejected the null hypothesis because the data told us to, but in reality the null hypothesis is true. That's what we call a type 1 error. Now how can that ever happen? Sometimes we get a sample that isn't representative of the whole population, and based on the data we see, that leads us to believe that the null hypothesis is false when in actuality it isn't. The probability of a type 1 error is your level of significance. Usually that's 0.05. So if you run a test and you reject HO, chances are you've made the correct decision because there's only a 5% chance you make a type 1 error, leaving 95% probability or chance that your decision is correct. So when we run a test and reject HO, we are usually confident that that's the right decision. On the other hand, if we run a test and we do not reject the null hypothesis, again, one of two things has happened. Either that's right, because the null hypothesis is true, or we've committed what we call a type 2 error. And you might say, well, why don't you fix the probability of a type 2 error to be small, like 5%? Unfortunately, the probability of a type 2 error is complicated, and we can't just fix it to be a small number. It's related to the probability of a type 1 error. It's also related to the sample size. So when people run statistical tests and don't reject the null hypothesis, that is, the data do not tell them to believe what they thought was true, the research hypothesis, usually people make weaker statements and say things like, we just don't have enough evidence to show that the null hypothesis is false. Because it could be very likely, high probability, that we're making a type 2 error. Now, type 2 error is related to power. We often see in papers, it's possible that my study was underpowered. And that comes up. Power is 1 minus the probability of a type 2 error. So if people are in the situation where they don't reject the null hypothesis and they thought they might, it could be that their sample size was just too small. And that is another way of saying that the study was not sufficiently powered. It didn't have enough size to detect what might be a real difference. So let me just walk through a few formulas for you. Again, on the exam, you're not going to be expected to have memorized lots and lots of formulas. I just want to show you the way these formulas work, and hopefully you'll get a feel for some patterns in the formulas. So if you have a continuous outcome, blood pressure, cholesterol, things like that, and you're estimating this particular continuous outcome in one sample, then the formula that you use for a confidence interval is one of these two. Oftentimes people use the second one regardless of the sample size, but sometimes when these are presented to people, they're distinguished by the sample size. If you have a large sample size, people often say take the sample mean plus or minus a z-score for whatever confidence level you choose times your standard error. The standard error is now s over square root of n, the sample standard deviation over the square root of n, the sample size. If the sample size is less than 30, then we use the t distribution, which is sort of like the z distribution. It looks like the bell-shaped curve, but it's flatter and the tails are thicker, and it's used for small sample sizes. You can calculate a t-value for your exact sample size, either from a statistical computing package or with a table. So here's a little example. Suppose we're calculating a 95% confidence interval for the mean waiting time at an emergency department. We sample 100 people. Among our 100 people, they wait about 38 minutes, and the standard deviation is about 9.5 minutes. So I've calculated those summary statistics. Now I want to take those summary statistics and convert them into a 95% confidence interval for the mean waiting time for all patients seeking care at emergency departments. So in this case, I'm using the first formula because my sample size exceeds 30. So it's 37.85 is my sample mean. The z-score for a 95% confidence interval is 1.96. The standard deviation is 9.5, and I divide by the sample size, square root of the sample size, 100. So sometimes people will present the confidence interval as 38 minutes plus or minus 1.86 minutes. So that's my best estimate for the waiting time is 38 minutes, plus or minus 1.86 minutes. That's my margin of error. Or you can take it to the last step, add and subtract the margin of error, and make a statement like, I'm 95% confident that the mean waiting time is anywhere from, let's say, 36 minutes to 40 minutes. Just a reminder, what we're saying here is it's possible that the average waiting time is anywhere from 36 to 40 minutes. Any of those times are possible. And I should also say that any time in that interval is as likely as any other. So it's not that we're most likely to see 38 minutes. That was just one sample. Now, the margin of error, the 1.86, is made up of two things. The z-score to reflect 95% confidence, and then our standard error, s over square root of n, represents sampling variability. I just made a note that when you do analysis by computer, it always uses t, and it just makes the adjustment for the sample size. If you have a large sample size, even if you're using t, t essentially turns into z as the sample size gets large. Suppose we were looking at a similar application where we want to estimate something, but our outcome is no longer continuous, but it's dichotomous. Say we're estimating the likelihood that people have good results from a particular surgery, the likelihood that someone goes into remission from cancer, and we have one group. So now the data that we have on each person are in the form of yes, no. So all that we have is our sample size and then the number of positive responses, and we take those and convert them into what we call a sample proportion. So we're just taking the number of positive responses over the sample size. And we can calculate a confidence interval. And here's the formula for a confidence interval. You start with your sample proportion, add and subtract the z-score to reflect whatever your confidence level is, and multiply by the standard error. Now here, there's no t version of this. If your sample size is small, and we define small for dichotomous variables as fewer than 5 successes in either group, or fewer than 5 events, let me say that, in either group. So if you had an application and you took 50 people and only 3 of them had an affirmative response and 47 had a negative, you wouldn't be able to use this formula because it wants you to have at least 5 in each of your 2 groups. It doesn't mean you can't analyze that, but you shift over to what are called exact procedures, and those don't have closed forms, so you have to shift to using the computer for those calculations, but you essentially get a similar result. So here's an example. In the Framingham Heart Study offspring study, we had 3,532 people. Turns out 1,219 of them were on antihypertensive medicine. So the outcome that we're looking at is use of antihypertensives, yes or no. So this is a dichotomous variable, so we're going to estimate a proportion based on this. And we're going to do a 95% confidence interval. Here with 3,500 people, we more than satisfy the minimum numbers of events and non-events. And so here's the calculation of my confidence interval. And again, I can present it in either of those last two, with either of those last 2 lines. But just to go to the bottom line, I would say I'm 95% confident anywhere from 33% to 36% of the patients are on antihypertensive medicines. So now, suppose we wanted to do an analysis, again, looking at continuous or dichotomous variables in one group. And if you only have one study sample and you want to do a hypothesis testing procedure, what you're comparing against is what we call a historical control or an external control. So on the left side of this slide, if we have a continuous outcome, we might ask the question, looking at people in 2015, is their average blood pressure higher than what it was in 2014? Well, we might know from census data from records what the mean systolic blood pressure was for patients in 2014. So that would be our null hypothesis, and then we can put as our alternative that our mean blood pressure in 2015 exceeds that value. On the dichotomous side, we might be looking at, let's say we had data from the CDC looking at the proportions of patients who meet the criteria for obesity. We know what those figures are, say from 2000, we're 15 years later. Has the proportion of patients who meet the criteria for obesity gone up? So we'd know what it was before, and we'd ask if there's an increase. And again, you're taking your sample data, either the sample mean that you observe when you're looking at a continuous outcome, or your sample proportion when you're looking at a dichotomous outcome. You have to standardize that. You convert it into a z-score, and then based on the magnitude of that z-score, you decide whether your data are in the middle of what's plausible under the null hypothesis or if they are extreme. And again, generally the comparisons are made based on p-values. If you have a one sample application again, but you're comparing against a historical control and your outcome is either categorical or ordinal, then you use what's called a chi-square goodness of fit test. I'm assuming that you've seen these things before, and I'm not going into great detail on these, but I just want to remind you of what test is done when. So if your outcome is categorical or ordinal, then, and you have one sample, one study sample, you would use a chi-square goodness of fit test. When would you ever do something like this? Let's suppose taking that, that CDC data again. We know from previous reports, the CDC tells us what % of patients are, let's just say, normal weight, overweight, or obese. That's an ordinal variable. We might know, based on lots and lots of data, what % of the population is estimated to fall in each of those 3 categories. We could ask the question, do those percentages hold up today in 2015? So we know the reference values, the percentages that were available, and now we take a sample in 2015 and see if we see similar proportions lining up in those categories. The chi-square statistic that's showing at the bottom of this slide, it looks at the observed frequency, that's the O, those are your sample data, and compares those against what you would expect based on those published distributions in each of your response categories. So if the observed data, your sample data, line up with what you would have expected based on reported figures, then this chi-square value is going to be small. If the chi-square value is small, you don't reject the null hypothesis because your observed and expected are close in magnitude. But if your observed and expected are very different, the chi-square value is going to be large. That's going to lead you to reject the null hypothesis. And again, if you ran this by computer, you'd get a p-value. A large chi-square statistic is going to produce a small p-value, which tells you to believe the alternative hypothesis. A more typical application is when you're comparing groups. And suppose we have an outcome that's continuous, two independent, again, physically separate groups. And so here what you have measured on each person is some continuous outcome, and then you summarize each of your groups, and I'm just calling them groups 1 and 2, the sample size in each group, the mean in each group, and then either the sample variance, that's the S squared, or the sample standard deviation, the S, in each of your groups. So these kinds of situations can arise from a cohort study. We have a group of people who meet certain criteria, and then you might separate them into different groups, group 1 and group 2, maybe by sex, maybe by exposure to something, maybe by their having a certain risk factor, hypertension, high cholesterol, and then you measure the outcome of interest that you're interested in. Again, it's some continuous variable. You can also give rise to these kind of data through a clinical trial, a randomized controlled trial, where you have people who meet your criteria. You impose the groups by randomization. Some might get treatment 1, some treatment 2. That might be an active treatment versus a placebo, or an active treatment, experimental treatment against something that's standard of care, and your outcome is continuous, so you're comparing the means on the two groups. Lots of formulas here. Again, you're not meant to memorize them. I just want to show you the structure of them. When you have continuous outcomes, you focus on the difference in your sample means. So that's x bar 1 minus x bar 2. That's the difference in your sample means is your best estimate of what you think is the difference in population means. Everything to the right of the plus minus is margin of error. I've got a Z formula and a T formula, again, for large and small samples. Again, it's fine to use T throughout. I just want to point out this SP term, which you may have seen before. It's what's called the pooled estimate of the common standard deviation. In our formulas, what we have is a weighted average of the two sample variances to get an estimate of the variability in the outcome, pooling data from our two groups. If you're doing a hypothesis test and you have a continuous outcome in two physically separate groups, this is what people often refer to as the unpaired or the two-sample t-test. You're comparing the means on this continuous outcome between the two groups. You can write the null hypothesis as the means are equal, or another way to say it is the difference is 0. And the alternative can be that the mean in the first group is larger than that in the second, it's smaller than that in the second, or they're just different. The last situation is called the two-sided test. Often that's the one that we're interested in. We might have a feeling about what direction any change is going to go, but just to be safe, we often do what's called a two-sided test and test the alternative that there's just a difference in the means. And here are your test statistics. Again, you start with the difference in your sample means as your basis for comparison, and then you look and see how big is that difference in sample means, and you have to factor in the variability of the outcome that you're dealing with. That comes through your pooled estimate of the variability and your sample sizes. Everything in the denominator of this test statistic is called the standard error. So here's an example. A clinical trial is planned to show the efficacy of a new drug against a placebo to lower total cholesterol. What would the hypotheses be? So here, P refers to placebo and N refers to new drug. So the hypotheses, the null hypothesis is the same in each of them, that there's no difference. So I just want, this is a little tricky in the way I set it up, but if you saw lower and went to number 2 because it has a less than sign, just be careful, because what we're trying to show here is that people who got the new drug had lower total cholesterol. So just because of the way I've organized my groups, I'm presenting the placebo, mean on the placebo first. That's represented by the first response. So the mean on the placebo is higher than that on the new, wants to be the response that, or the hypotheses that you're testing. Again, just be careful when you're setting things up, the order in which you present the groups, because that can impact the hypotheses. If you have a dichotomous outcome and are comparing two groups in terms of some indicator variable, you follow the same approach, and you could either do a confidence interval estimate for the difference in proportions. Again, don't get bogged down in the details of the formula. Start with your difference in sample proportions. That's the P1 hat minus P2 hat, plus or minus the standard error. Again, all of that to the right is getting a handle on sampling variability. Now, when we're dealing with a dichotomous outcome, there are actually several ways to make comparisons of proportions. And this comes up in EPI a lot. In fact, you probably talk about this idea much more in EPI than you do in Biostat. But if you have a dichotomous outcome, so a yes-no variable, we often code that for analysis as what we call a 0-1 variable. And I probably should have written it the other way. Oftentimes when we have data like this and we put them into a spreadsheet, we use 0 for the no response and a 1 for the yes response. We use the term risk to represent the proportion of successes. That's another way to label our sample proportion. It's based on the number of people who have the outcome of interest. That's X divided by our sample size. So a risk is a proportion. It's the ratio of part to whole, X to N. An odds is a ratio of successes to failures. So the odds of an outcome is calculated by putting the number of people who have the outcome in the numerator to the number of people who don't have the outcome in the denominator. Notice the difference in the denominators. The risk is, in both cases, you have the number of people who have the outcome in the numerator. For the risk, the denominator is everyone. For the odds, the denominator is people who don't have the outcome. And so when we compare groups, we can, we could make the comparison. For some reason, this image is not displaying. I'm sorry. But I'll tell you what the odds ratio is. The risk difference is just the difference in proportions. The relative risk is the ratio of the two risks. The odds ratio, and I'll fix this before we post these slides, is in the numerator P1 hat divided by 1 minus P1 hat. That's the numerator. In the denominator, it's P2 hat over 1 minus P2 hat. So you have an odds in the numerator divided by an odds in the denominator, and that's an odds ratio. Now, there are different situations in which we use relative risks to make a comparison versus odds ratios. The relative risk is a much more intuitive measure of effect. The risk difference is also a useful measure of effect. The odds ratio is kind of a weird measure of effect, but it turns out it has some really nice properties. And so under certain study designs, and you may remember this from EPI, if you have a case control design, it turns out that the odds ratio is the only measure of effect that you can calculate. And so it becomes a very useful measure to compare proportions. And again, I'll fix this before we post these slides. But if you want to do a confidence interval for a relative risk, a minute I showed a lengthy formula for a confidence interval for a risk difference, you can go ahead and do that. It turns out, though, to follow the same approach that we've been using, which is point estimate plus or minus margin of error, it turns out to follow that same approach and using a z-score to represent the confidence level that you've chosen, you have to put everything on the log scale. This is a technical detail. All of this would be done internally to the computer if you're doing it by computer. But essentially, there is a formula that you can use, and you end up exponentiating what you get from that middle formula so that at the end, you can say something like, I'm 95% confident that my relative risk is between this value and that value. The same is true, or you follow the same approach for the odds ratio. Again, technical details, you won't be expected to regurgitate or use these kinds of formulas, but you'll want to know what's the difference between a risk difference, a relative risk, and an odds ratio. You can also do hypothesis testing if you're comparing dichotomous outcomes in two independent groups. The null hypothesis is that the two proportions are equal. The alternative is that one exceeds the other, or that they are just different. And again, usually it's the case you have a sense of what the direction of the transition might be, but we almost always do a two-sided test to guard against things going the other way and us not being able to detect them. So let me try to bring this back to reality a little bit and show you a paper. So this is a table that was out of a paper comparing two groups, treatment group and control group. And what we have, this happens to be a study looking at neonatal outcomes. And we've got almost 500 babies in each of the groups. And what we're shown in this table, first are birth weights for the babies in each of the groups. And we're seeing here the mean birth weights in grams and then a standard deviation in grams for each of the groups. Now just sticking with birth weight for a minute, birth weight is a continuous variable. And so there is a relative risk column, but that doesn't apply for continuous variable. That comes in when we're looking at indicator variables. So we'll come back to that in a second. So to make the comparison, or to answer the question, are the birth weights statistically significantly different between the two groups, one thing we could do is look at that p-value. That's a very small p-value, suggesting that there's statistical significance. That p-value was based on a two-sample t-test because it's a continuous outcome, birth weight, and we're comparing two independent groups. Another thing that could have been done is calculating a confidence interval for the difference in birth weights. So back a few slides, I gave you a formula for a 95% confidence interval for the difference in means. Using that formula, I get a 95% confidence interval for the difference in mean birth weights of negative 175 grams to negative 37 grams. Now, the way I took my differences is I did treatment group minus control group, so everything is negative. I could have done it the other way, just take the differences the other way, and I could say I'm 95% confident that the difference in mean birth weight is anywhere from 36 to 175 grams, with the babies in the control group being heavier. Either way works fine. Now, one thing I just want to point out, when you do a confidence interval for a difference, if the null value, now what I mean by the null value is the no difference value, if the null value is in the interval, that suggests no significant difference. Well, when you're comparing means in two groups, the null value is 0. So the fact that 0 is not in that interval tells us that there's a statistically significant difference in mean birth weight. The p-value confirms that by way of a hypothesis test, but you can judge statistical significance with a confidence interval by looking for your null value in that interval. So now let's move to some of the other variables that are shown in the table. The rest of the variables, for the most part, are indicator variables. Birth weight over 4,000 grams, large for gestational age, fat mass is continuous, but preterm delivery, small for gestational age, and so forth. So here the authors are showing us the number of babies that meet the criteria in each group divided by the sample size. Now notice the sample sizes aren't always 485 and 473. That just means that there's some missing data. Some people didn't get measured on certain things, or these data weren't available. It's not too extensive, so that doesn't suggest a problem with the data. What they're showing us in terms of comparing the groups is a relative risk. So for example, let's look at birth weight over 4,000 grams. In the treatment group, about 6% of the babies had birth weight over 4,000 grams. In the control group, about 14% of the babies had a birth weight over 4,000 grams. If you calculate a relative risk, now in this case they've put the treatment as the numerator and the control group as the denominator. So the relative risk comes out to be 0.41. And they give us a 95% confidence interval from 0.26 to 0.66. So that's the possible range for this relative risk, and they're giving us a p-value of 0.0001. So what they're saying with that relative risk of 0.41 is that the ratio of those with, let's just say, large birth weight in the treatment to the control group is 0.41. So fewer than half of the babies in the treatment group have large birth weight as compared, or the ratio of those who have large birth weight, treatment to control, is 0.41. So it's almost half the babies in the treatment group compared to the control group meet that particular criteria. Now, to judge whether that difference that we're seeing in the percent who meet the large birth weight criteria is significantly different, we could look at that relative, the confidence interval for the relative risk, and now you have to think, what's the null value? Well, for a relative risk, if the two proportions were equal, then the relative risk would be 1, because the relative risk is the ratio of the two. 1 is not in there. That suggests a statistically significant difference. The p-value is also significant, which is consistent. Now, if you have a continuous outcome in two matched groups, then you don't use the two independent sample t-tests. You use what's called the paired t-test. And in fact, what you do is you calculate different scores for each person. So the summary statistics that you put together are the sample size, the mean difference, and the standard deviation of the different scores. And I'll show you what I mean by that. So the little subscripts D just refer to the fact that these are based on different scores. So this is the kind of data that I mean for a matched or paired design, where you might have an identifier, a unique identifier assigned to each person, and you have two measurements done serially in time. So person 1 gets a 55, you presumably do something in between time, and then a second measurement of 70. And then the second person starts at 42, you do something, and then they're at 60. And what you do is you calculate different scores for each person. These kind of data can also arise in what's called a crossover trial. A crossover trial starts with people generally randomized to a first treatment. So in this graphic, what I'm saying is we have a group of people, maybe there are 100 of them. 50 get the treatment and 50 get the placebo. You take a measurement after the requisite amount of time. And then people cross over to the other treatment, meaning that people who first got the treatment then get the placebo. So you take a second measurement on each person, once under the treatment and once under placebo. And you do the opposite, or the same thing I should say, but in opposite order for the other group. First under the placebo and second under the treatment. So you have two measurements on each person. And so this is where, again, you take different scores and look at how those different scores looked as a means of comparing the groups. You can make the comparison with a confidence interval, and you'd get a confidence interval for the mean difference. Now, I'm using my words carefully here. These formulas on this slide are showing formulas for a confidence interval for a mean difference, as opposed to a difference in means. The latter is used when you have two independent groups. You calculate a difference in means. This is a mean difference. You can also run a hypothesis test in this scenario. The null hypothesis might be that the mean difference is 0 against the alternative that there's been an increase, a decrease, or some difference over time. Again, the form of the test statistic is look at what your observed difference is in your sample and then standardize that so that we can put it on some common scale and interpret it. Once again, you could put this into a statistical computing package and get a p-value to decide whether your observed difference is significant or not. Here's an article coming from a paper, and we're looking at changes in primary and secondary outcomes at 1 year from baseline, and here they have two groups, a control group and an intervention group. And what they're showing here is, in the first two columns, change from baseline. So this one's a little complicated. So we have a baseline measure, and then we have a follow-up measure. One group didn't have anything happen in between. The other had an intervention. So here we have change scores running down the column. So for example, if you look at the control group, the first group, you get a change in weight. And the authors here are showing us the median change in weight. There must have been some outliers or extreme values in terms of weight change in the control group. So they're showing us the median change, and it looks like people in the control group gained on average ½ pound. over the period that they were observing. Whereas people in the intervention group lost on average 2.5 pounds over time. So those are mean differences within each group before versus after. Now if you jump to the column second from the right, we're looking at intervention effect. Now we're comparing the changes across groups. So now we're comparing the change we saw in the control group to the change we saw in the intervention group. That the intervention effect is looking at differences in means using the unpaired confidence interval. And the test in the far right, now they're saying it was based on a rank test if you jump right to the bottom. So they're using what's called a non-parametric test because they're concerned about outliers. But just in general terms, the idea is, I just want to be clear between within the groups, it changes over time in the same people. So you're using paired tests that account for the repeated measures within the same people. And then when you compare across control versus intervention, then you're doing unpaired tests. And you really have to get that straight. Is it the same people measured twice, or is it different groups of people in different, in this case, in different treatments? Then it's unpaired tests. And that's a very common mistake that people make when they do analysis and interpret analysis. Again, the p-value summarizes statistical significance. And I mentioned before that you can actually judge whether a difference or a comparison is statistically significant from using a confidence interval. So you might say, well, why would you ever do a hypothesis test at all if you can judge statistical significance with a confidence interval? Well, the p-value summarizes your exact significance, just how significant is the difference or what you're seeing in your data. The confidence interval only allows you to say that a result is statistically significant, yes or no, but not how significant. The confidence interval also gives you an idea of the magnitude of effect. How big is the difference? What's the difference in means actually look like? Not around how statistically significant, but what does the actual difference look like? In many cases, you want both of these things. Another point that I should have made earlier on is that there's a difference between statistical significance and practical or clinical significance. Something can be statistically significant based on a p-value, but not practically different. So for example, you might have a study where you do a clinical trial, people get an intervention versus a placebo, and maybe you're looking at incident disease over time, and people in your control group are statistically significantly worse off than people in your intervention group. But when you look at the data, maybe it's 1% of the people in the control group got the bad outcome versus 0.5% of the people in the treatment group. Yes, that's half, but the percentages are so small they may not be clinically meaningful. So you always want to look at statistical significance and clinical or practical significance when you're judging data. So just a few quick questions. The null value of a difference in means would be what? So here it would be 0. Anytime you're looking at the difference, the 0 value for a difference would suggest that the groups are the same. So that's what our null value represents. The null value of a mean difference, and you might be thinking, didn't you just say that? Difference in means is for unpaired, mean difference is for paired. Again, because it's a difference, 0 is the null value. The null value of a relative risk would be a 1. That would suggest that the proportions are the same. The null value of a difference in proportions. Lots of times people get this wrong, thinking proportions is always 1. But if you're taking a difference, this is a risk difference, even though you're taking a difference in a different quantity, the null value is still 0. And then lastly, the null value of an odds ratio, that would be 1. So anytime you look at a confidence interval, for example, for a relative risk or an odds ratio, look to see is 1 in there. That will tell you if the difference is statistically significant or not. If you have a confidence interval for a difference, look to see if 0 is in there.
Lisa, we do have one question which might fit into this section.
Okay.
The question is, if we have skewed data, should we use median versus mean values to calculate Z or T scores?
Yeah, if you have, that's a good question. If you have skewed data and you're reporting the median, like that paper did, there's actually a whole different category of statistical tests. They're called non-parametric tests, so there's no more Z's and T's as part of that. So you use what are called non-parametric tests, which are essentially based on ranks in the data. And so it doesn't come down to those Z and T formulas that I showed earlier. Those were all for when you're comparing things on the basis of means because you've judged there to be no outliers. Hopefully that's sufficient. If not, please send in another question. Okay, so the question that's on the slide, a two-sided test for the equality of means produces a p-value of 0.2. Would you reject HO? Now, hopefully you said no, although the answer could be maybe. If you remember the way you judge a p-value, if the p-value is less than your level of significance, which you choose, then you would reject HO. So if you chose a level of significance greater than 0.2, then your answer would be yes, but we never do. We usually choose a level of significance in the ballpark of about 5%. So that's why I'm saying in this case no. So the next couple of slides I'm going to go over quickly because we can get caught in the weeds in here. Hypothesis testing for more than two means. So here you have a continuous outcome, but you have more than two groups. So it could be in a clinical trial where you have a continuous outcome, but you have, say, your experimental treatment, a placebo, and an active treatment being compared all at the same time. So the null hypothesis is that, I'm just using K as a placeholder, the K means are equal against the alternative that they're not. It's a complicated test statistic. All you need to know it's an F statistic. It's not a Z or T anymore because now that we're going beyond two groups, we have to shift to a different procedure. Essentially, that messy F statistic is making is a ratio of estimates of what we call between treatment variability to error variability. Now, this table I'm sure is not very clear, but I'm just reminding you, I hope, when you do these calculations and you run them through the computer, it spits out what's called an analysis of variance table, where essentially it's looking at the variability in the data and it's partitioning it to that due to your treatments versus error or residual. And if there's a lot of variability that can be attributed to the treatments, then we say there's a significant treatment effect. And again, you'll get a p-value if you do this analysis through the computer, and you can judge statistical significance on that basis. Just a few things about analysis of variance. Again, you use it when you have a continuous outcome and more than two groups. If the sample sizes in your groups happen to be equal, and they don't have to be, the design is just said to be balanced. That's all. And balanced designs give us the greatest statistical power and are more robust to violations. So we're always assuming that our outcomes follow generally a normal distribution. That doesn't always happen. Data aren't always perfectly normally distributed. It turns out many statistical tests work well anyway. But if you have control over an experiment and you can make sure that your sample sizes are equal in the groups, that's the best way to go because that protects you against lots of bad things happening with the analysis. When we do an analysis of variance, say we have 5 groups, we run the analysis of variance and we reject the null hypothesis, all we can say is that the 5 groups aren't equal. Then people often do a series of tests following that analysis of variance to say, well, which groups aren't equal? And they do what are called multiple comparison procedures. Let me make this simpler. Say we have 3 groups. We run an analysis of variance and we find significance. We then might ask, well, is group 1 different from 2? Is 1 different from 3? Or is 2 different from 3? We could make those comparisons with 3 unpaired t-tests. The problem is every time you run a test, there's a 5% or whatever you choose chance that you make the wrong decision. And so instead of running a series of t-tests, which can build up the chance of a type 1 error, we use what are called multiple comparison procedures. And these are a sets of tests that can be used to run what we call post hoc tests after you find that the groups aren't all equal. And they're set up to protect you against an increased type 1 error rate. And there are many of them. There's the Tukey test, Chaffee test, Duncan. They're named after people, all of them, or most of them. But you may have seen some of these things. And again, just in principle, you use these so you don't run up the probability of a type 1 error. Some of you may have seen what are called higher order analysis of variance, two-way ANOVA, three-way ANOVA, where instead of just one treatment variable, you might have a clinical trial where, say, you have people who get an experimental treatment, the placebo, and what's considered standard. You might think that the treatments are differentially effective in men or women. So now you have a treatment effect and you have a sex effect. And you can test both of those things in one experiment where you test in using what's called a two-way ANOVA, test to see if there's a treatment difference, a sex difference, or both, the interaction between the two. And then there's lastly something called repeated measures analysis of variance. This is taking our paired t-test more general, where you have more than two groups and repeated measurements over time. The paired t-test is just one group repeated twice. Here we can take more than two measurements, and we can also handle multiple groups with more than two measurements. It gets complicated, but the gist of it is more than two measurements. Chi-square test of independence, this is something that you've probably seen a fair amount. It comes up a lot. It can be used to test whether there are differences, associations between dichotomous, ordinal, and categorical variables. And it is used in the setting of two or more samples. And the question that we're asking is whether the distribution of the outcome being a dichotomous, ordinal, or categorical variable, is independent, unrelated to the groups. And again, we use this chi-square statistic looking at observed and expected frequencies. It might be easier to see this the way the data are organized. If you have data organized this way, where you have an outcome, I'm just saying there are three responses to the outcome. There could be two. It could be a yes-no outcome with just two columns. And those 1, 2, 3 could be ordered or unordered. And suppose we have three groups. What we're asking here is the distribution of the outcome different across the groups? So the percentages I put in, so look at Group A. In Group A, 20% of the people are in response category 1, 40% each in groups 2 and 3. Whereas in Group B, it's 50% in Group 1 versus 25-25. And in Group C, almost everybody is in category 1. This would be a situation where there's definitely an association between the outcome and the group. So we analyze this with a chi-square test of independence. So here's a table showing some demographic data on patients who participated in a study, and it's a study of antenatal corticosteroids. People got either weekly courses of steroid or a single course, and we have p-values over on the right. So let's just look at some of the outcomes. So let's look at the second one down, gestational age at randomization. That's measured in weeks, and they're showing us the mean and the standard deviation in parentheses. And then they have a p-value over on the right of 0.13. What test was used to produce that p-value? So this is where you have to think, what kind of variable is gestational age? Well, that's a continuous variable. And how many groups do we have? 2, weekly and single. And I know I'm not giving you a lot of background, but people got either the weekly courses or the single courses, so this would be the unpaired t-test. Now let's look at race ethnicity. They show us the distributions for the women who are in the weekly group and then in the single group, and then we have a p-value of 0.74. What test was used to produce that value? So again, you have to think about what kind of outcome am I dealing with. Race ethnicity is a categorical variable, and we have two groups, weekly versus single. So that p-value of 0.74 came from a chi-square test of independence. It's like that table I was showing a minute ago, but rather than it being a 3 by 3 table, it would be a 2 by 4 table. the groups, 2 groups versus the 4 outcome categories. Okay? So I've just got a series of practice questions for you that we can run through quickly. Or let me ask you, Erin, maybe I could post these practice questions and get to the regression analysis. Can I ask for your advice given the hour?
How many questions are there, Lisa?
There are 12.
You know, if we can, I think we can go through them. Right now we don't have any questions, so this can go into our Q&A time. So I think we'll be okay if you want to run through them. I think they're important.
Yep, okay. So no questions either means that you're all asleep or you're all good with this. I hope it's the second one. So I just put together a series of questions. These are just practice questions. And I think really, certainly when I teach the Intro Biostat course, this is what I hope people can do with it once they finish it. So I hope this is useful to you. So in the Framingham Heart Study, suppose we want to look at risk factors for impaired glucose. So our outcome is glucose category. People are classified as either having diabetes because their glucose is 126 or higher, having impaired fasting glucose because they're between 100 and 125, or normal glucose. So that's our outcome. And we're looking at 4 risk factors: the sex of the person, the age of the person in years, their BMI, and people are in normal weight, overweight, or obese categories, or their genetic history. So really try to think about these as I put them up, because I do think these are questions of the flavor that you might see. So what test would you use to assess whether sex is associated with glucose category? Or another way to say that, whether the glucose categories are different for men versus women. So the correct response would be the chi-square test of independence, because glucose category was the 3 different categories, happens to be ordinal, and we have men and women, and so this would be along the lines of that table that I showed you just a minute ago, but we'd have a 2x3 table. So chi-square test of independence. If you thought ANOVA is for a continuous outcome, so that wouldn't happen here. Chi-square goodness of fit is when you have some reference values that you're comparing against, and test for equality of means would mean exactly 2 groups with a continuous outcome, and our outcome here is the categories. What about whether age is associated with glucose category? Another way to say this is there a difference in ages among the different categories? So this one would be analysis of variance, because we have the 3 glucose categories, but age is continuous. So we'd be comparing mean ages across the 3 categories, so that would be analysis of variance, which you use once you get past 2 groups. What about BMI and glucose category? Now here you have to think, how are we operationalizing BMI? So this one would be chi-square test of independence, because BMI is in categories. Now if BMI was left as continuous, as it is sometimes, then this would be ANOVA, just like we did for age. Now suppose we have the same risk factors, but our outcome is different. Now suppose the outcome is fasting glucose level. So now we're measuring the absolute glucose level in participants. How would we see if sex is associated with glucose level, or if there's a difference in glucose levels by sex for men versus women? So this one would be an unpaired t-test. The outcome is continuous glucose level, and we have the 2 groups, men versus women. How about BMI? Again, think of the way we're modeling BMI and glucose level. So this would be ANOVA, because BMI is measured in categories. We have 3 categories, and glucose is continuous. So again, you've got to get all these tests kind of organized in your mind. When do you do what kind of outcome, continuous, dichotomous, and so forth, and that dictates the kind of test that's used. What test to compare age and glucose level. This one's actually not fair. We haven't gotten to that yet. This one, age is continuous and glucose is continuous. So we'll get to that in a minute. If you're thinking ahead, this would be a correlation or a simple linear regression analysis. But I'll review that with you in just a second. Suppose now that we have a third outcome, diabetes versus no diabetes. Same risk factors, but a different type of outcome. How would we test whether sex is associated with diabetes? This one would be test of independence. So now we have sex is male, female, diabetes is yes, no. You'd have a 2-by-2 table. Another way you could do this is actually do a test of proportions. When you have exactly two groups and a dichotomous outcome, you can also do a test of proportions. But the test of independence also works for just two groups and exactly two outcome categories. BMI in diabetes. This one will be chi-square test of independence because we have the 3 BMI categories and then our diabetes yes, no. And lastly, age and diabetes. This one would be a test for equality of means where you're looking to see is the mean age different in participants with and without diabetes. So I think those are good questions to review and sort out in your mind. I know I went through them quickly and it's at the end, nearing the end of a long session, but you might take a look at those again and try to organize those for yourself. So last little section here, correlation and regression. So the correlation coefficient is R, lowercase r, and it measures the nature, what I mean by nature is direction, positive or negative, and strength of the linear association between two variables. And I should say two continuous variables. So our range is from -1 to 1. The sign of it, positive or negative, indicates the nature or the direction of the association. And the magnitude indicates the strength of the association. So if R is 0, that indicates that there's no linear association between two variables. If R is closer to 1, or it's on the positive side, that suggests that the two variables are positively correlated, as higher values of one are associated with higher values of the other. If the correlation is negative, that suggests that higher values of one are associated with lower values of the other. So we often do correlation analysis just to get a feel for how variables are related, the direction and the strength. Regression analysis takes it one step further and actually maps out the equation that best describes the relationship between two continuous variables. And we talk about simple linear regression, not because it is simple, but simple refers to the fact that you have one predictor variable. So when we have regression analysis, we usually use Y to denote our dependent or outcome variable, sometimes it's called response variable, and X to indicate or to denote our independent or our predictor variable. So the simple linear regression equation is the third bullet, Y hat, the little hat over it just means predicted value of Y, is equal to B0, which is the y-intercept, and B1, which is the slope. The y-intercept is the value of Y when X is 0, and the slope represents the change in Y relative to a 1-unit change in X. Again, backing up a little bit, big picture, when do you use this? When you have a single continuous outcome and a single predictor variable. Now that predictor can be continuous. It can also be dichotomous. It can be the sex of the person, for example, in which case the slope represents the difference in means between your two groups. There are assumptions for linear regression. First, that is that a line well describes the relationship between the predictor and the outcome. You have what we call independence of errors. That is, in English, that we have people that are independent in the sample. You don't have the same person repeated multiple times, not repeated measurements on people. Homoscedasticity talks about constant variance in the outcome over the range of the predictor. And then the outcome should be normally distributed, essentially, at each value of the predictor. Multiple linear regression comes up when we want to examine the effect of several predictors simultaneously on our outcome. So we still have one outcome variable, y, and it's continuous, and then we have a set of predictor variables. And the multiple linear regression equation is at the bottom, and y hat, again, is the predicted value of y. B0, it's no longer the intercept in the same way because now we're beyond a two-dimensional representation, but B0 is the value of y when all the x's equal 0. And the B1, B2, all the way out to however many predictors you have, sometimes people call those slope coefficients or regression coefficients. They represent the change in y relative to a one-unit change in that predictor, holding all the other predictors constant. So the multiple regression model is what we call a conditional model. As we interpret each of those slope coefficients or regression coefficients, it's assuming that all the variables are held constant. So they're in the context of other things being considered. So when you're evaluating or doing a multiple regression analysis, there's a couple of steps that you walk through. The first is you do an overall test. You ask the question, is this set of predictors related to the outcome, the whole set taken together? And if the answer to that is yes, then you move on to looking at individual predictors. And you assess whether each of the individual predictors is significant or not. And sometimes you're interested in the relative importance of the predictors. So I happen to work on the Framingham Heart Study, and we might be interested in what are the predictors of blood pressure, high blood pressure in particular. So if we're looking at systolic blood pressure as the outcome, we might be looking at a number of things: the age of the person, the sex of the person, how much exercise they do, whether they smoke, and things like that. We might be asking, are these things significant, and then which of them is most significantly related to the outcome? And you can make those judgments on relative importance by p-values, because those are all on the same scale, or by what we call standardized coefficients, which again standardizes each of the predictors, so you're comparing apples and apples. In multiple regression analysis, and also in simple regression analysis, the predictors, the x's, can be continuous. They can be indicator variables, so you could create an indicator for sex. So you could have male sex, for example, where 1 is if the person is male and a 0 is otherwise, or in other words, if they're female. Or they can be a set of dummy variables. You use dummy variables to represent categorical predictors in a regression analysis. So for example, if we had race ethnicity measured on a set of participants, and we wanted to enter race ethnicity into our multiple regression analysis, let's suppose just for simplicity we had people categorized as white, black, or Hispanic. I realize there are more races than that, but let's just say that. That's a categorical variable. To represent race in our regression analysis, what we would do is create 2 dummy variables. You always need one less than the number of categories you have. What you do is you create 2 indicator variables. You first choose one of your groups as the holdout group or the referent group. So suppose I keep white as the referent group. I then create 2 new indicator variables. One to indicate people if they are of black race, so people who are black will be coded 1 on this indicator black and a 0 otherwise. And then I'll create an indicator of Hispanic race, 1 for those who are Hispanic and a 0 otherwise. I don't need an indicator of white race. That's my holdout group. And if a person is scored 0 on the indicator of black race and 0 on the Hispanic, then they are by default white. So then in the regression analysis, I enter these 2 indicator variables, black and Hispanic, and that gives me a sense of whether there's a difference among the races. Confounding and effect modification come up with multiple regression analysis. And again, this comes up an awful lot in epidemiology, so you might have covered this extensively in epi. Confounding is the distortion of the effect of a risk factor on an outcome by something else. So again, in Framingham, we're often looking at variables that are related to cardiovascular risk factors. And if we look at the association between BMI, say, or blood pressure and cardiovascular risk, BMI could be a confounder. It could be that if we leave BMI out, we're incorrectly attributing an effect to blood pressure when it might have something to do with BMI, and vice versa. So a confounder can enhance the effect of a risk factor, or it can mask it. And so you have to look and see what's happening by digging in a little bit deeper. Effect modification is a different relationship between a risk factor and an outcome depending on a third variable. So I have an example of that in a second that I'll show you that might drive that point home. But here's an example first for confounding. So the left-hand side of this is a series of simple linear regression models. So the outcome is systolic blood pressure. On the left side, we have 4 simple linear regression models, first relating age to blood pressure, then relating male sex to blood pressure, BMI to blood pressure, and then blood pressure meds, whether people are on meds to systolic blood pressure. On the left side, those are a series of simple linear regression models. On the right side, that's one multiple regression analysis with all 4 things entered at the same time. Well, over on the left side, if you just looked at the association between blood pressure meds and systolic blood pressure, it looks like people who are on meds, their mean systolic blood pressure is 33 units higher than people who are not on meds. And that takes a second to digest. You think, well, shouldn't they be lower if they're on meds? But they're on meds because they were higher to begin with. When you look at the multiple regression analysis, now factoring in age, sex, and BMI, the effective blood pressure medication is actually smaller. That's because there's confounding due to age, sex, and BMI on blood pressure meds. Who are the people that are on meds? They tend to be higher. I'm not sure about a sex difference. They might also be carrying more weight. And so that's it. And when the unadjusted, based on the simple model, is different from the adjusted estimate of effect based on the multiple regression model, we say there's confounding. And this is an example of a clinical trial designed to raise HDL, that's the good HDL, and an example of effect modification. So here we have results of, or the mean HDL levels measured after getting the new drug or placebo in women and in men. So when you analyze this data with women and men combined, it looked like there was no effect of the drug at all. But when you separate it out, look at the women. The women who got the new drug had a little bit lower HDL than women who got the placebo, but not much at all. Versus in the men, those who got the new drug, their HDL was much higher, which is the intended effect, and versus those on the placebo. This is what's called effect modification. Depending on your sex, there's a different effect of the drug on HDL. And to get at effect modification takes digging in to the data in this way, and you actually have to know what you're looking for. You wouldn't just stumble on this unless you had some suspicion that there might be an effect due to sex. Very quickly, logistic regression is used when your outcome is dichotomous. Linear regression for continuous, logistic regression for dichotomous. Simple logistic when you have a single predictor, multiple logistic when you have several predictors. Again, you've got a complicated association here, but I'm sorry, we seem to have a traffic jam outside my office. With some algebra, the very bottom line says the log of the odds of the probability of having the disease, or the outcome in this case, is related to B0 plus B1x. So that right-hand side of that last equation looks like the more familiar multiple regression equation. So by doing that transformation, the log odds of the outcome is related to what looks like an intercept plus a slope. And that's why people do that algebra, so that the right-hand side looks like the regression equation. The same is true for multiple regression. The log odds of the outcome is related to B0 plus B1x1 and so forth, which looks like the multiple regression equation. Now, interpreting those regression coefficients, if you ran this, and you would have to run this by a statistical computing package, I've got a little example here where my outcome is birth defect, yes or no, and I'm relating that to whether the mother smoked in pregnancy, yes or no, and then the mother's age in years. So what you get are regression coefficients, that's the B column, and to interpret those, what people do is they exponentiate those. So if you exponentiate 1.062, you get 2.89. If you exponentiate 0.298, you get 1.35. Now those odds ratios are a little bit more interpretable, and what we'd say is the odds of a birth defect is 2.89 times higher in mothers who smoked versus mothers who didn't, holding age constant. So what people do is they get those coefficients and they exponentiate, and the odds ratios are much more interpretable. Last topic very quickly, and I'm not sure everybody has seen this in an intro class. Survival analysis is an analysis where your outcome is time to event. And again, I do work in Framingham where we look at whether people develop things like cardiovascular disease and stroke. And in addition to measuring whether they develop that outcome, yes or no, we also look at when they develop it. How long does it take? And so these kinds of analyses are called survival analysis. And we're looking to look for risk factors associated with longer survival. Now, the name of this sounds like we're always looking at survival, yes or no, death kinds of outcomes. And we're not. It's just that name was given to this because that's how it was derived. But the outcome can be any dichotomous outcome as long as we have a time measured to it. What's specific about survival analysis is we have incomplete follow-up information. And we have this issue called censoring, where for many people, we know their survival time, that is how long they survive, is actually greater than their follow-up time, because we can only measure them for as long as we study them. So all we know is how long people were free of disease. So in the Framingham study, there are lots of people, we might follow them for 50 years. And all we know is through 50 years they didn't have an event. And so the survival time is longer, so we have what we call a censored time. And so that takes special statistical techniques. And just to give you the names, we use what's called a log rank test to compare survival in multiple groups. And we can estimate survival curves. So time is showing on the x-axis, probability of surviving on the y-axis. Everybody starts at time 0 with probability 1. Everyone's alive at the beginning of your study. And the survival curve drops off over time. The more sharply that the curve drops off, the worse the survival is. And from curves like this, you can estimate, for example, the chance that someone might survive 2 years or 4 years or whatever by looking at the time frame and projecting it onto the y-axis. You can also compare survival curves, and the dotted line curve compares one treatment to the solid line curve, which is the survival in a second treatment. Survival is better in chemo after surgery, represented by the dotted lines, and that could be detected by what we call a log rank test. So survival curves that stay up near the top, higher probability of survival over a longer time, are better than those that drop down. And you can detect that statistically. You can extend those regression analyses. These are getting a little bit beyond what we tend to cover in the intro class, but you can extend those ideas of regression analysis to survival data with something called Cox proportional hazards regression, where you relate survival time to a set of risk factors. And just in case you've heard the term hazard ratios, are the measures of effect that come out of survival models. These are like odds ratios that are relating risk factors to likelihood of event when you have survival data. So that is a very fast review of the entire semester of Biostat. If you have any questions, I'm happy to stay on the line and answer any questions, and I hope you all do well on the exam.
Wonderful. Thank you so much, Lisa. If there's any questions, you can submit them now in the chat box. Okay, if there's no questions, then I think, Lisa, you covered it all, and everyone's fully prepared or needs to do some studying. So I appreciate your time. Thank you so much for sharing your expertise and your knowledge with us today.
Okay.
Again, Again, all of the presentations from the entire series from all 5 core subject matter will be posted on the NBPHE website, the slides as well as the webinar that's been recorded, so you can view them as you are studying and preparing for the exam. And we wish you all the best and the luck. And again, on behalf of ASBPH and the National Board of Public Health Examiners, thank you, Dr. Sullivan, for joining us today.
My pleasure. Good luck.
Bye-bye.
Bye.